Okay, if you have a complex problem, instead of delegating that task to one generalized agent, if you delegate it to many specialized agents, you will easily solve that problem. So that is the main core philosophy of this design pattern, where specialization is over the generalization. So that means instead of generalizing, giving task to one agent who is generalized at everything, delegate it to many specialized agents. So this is what we will be looking into. So we'll talk about the design, the architecture, the core idea of the design, and then when should we use this kind of design pattern, and then again the limitations, the trade-offs, and we'll see some bioinformatics use case, and most importantly we will do a hands-on where I will show you how we can quickly build this kind of multi-agent system where we have many specialized agent and will a team of specialized agent to solve any problem. Okay, without further delay, so let's start. So the multi-agent design pattern is like, the core idea is like, instead of building one overloaded generalistic agent, distribute your work across multiple specialized agents. That is, each agent focuses on what it does best. That's important, right? So that's how the flow looks like. Let's say you give a complex task to a main agent, that's the coordinator. So this agent knows like, okay, I have to solve this problem and I have a team of specialized agents. So this is more of a manager kind of thing, and he will distribute the work to specialized agent who are specialized tasks, and finally all the response from all the output will go to this agent, and that agent will decide. And it's not like that agent will always it's not like parallel, like it will have to call all these four agents. Depending on the task, it may call only one agent, or it may call 1, 2 and 3 agent and get the output. So it's up to the coordinator and manager, depending on the user's request, it will decide which agent to call and get the job done. So that's the advantage of this kind of system. And because this is a very, very autonomous intelligent system, because here the agent has the capabilities to call which teammates or which sub agents to leverage or use that. Okay, so we'll see how this works as well. So the pattern definition is like, multiple agents, specific roles, focused expertise, and each agent are equipped with their own tool capabilities. And we have a coordinator agent. That agent will route task to appropriate sub specialist, and then it will take the output, synthesize their output, and then it will interact to the user. So user will never interact with this agent. The user will interact with the coordinator agent or the manager, right? So the advantage is like, since each agent is special, right, you can completely focus on that agent. So make sure that you optimize that agent for that task, what he is best to do. And the other thing, like, if that agent is bad, something does wrong, you can replace and work with some other agent, so that capability, so you don't have to disturb that one single agent, right? So that's the good beauty of having separate agent. And again, cleaner prompt and simpler logic per agent, better handling of complex and multi-domain workflow. So basically you can targeted system prompts for that particular agent, and again you can have, let's say, one agent in bioinformatics domain, one for software, one for QA, one for those kind of thing. Each domain specific agents we can define. So that's what specialization beats generalization when complexity grows. Everything is simple, then this one model is enough, one agent is enough. But when it becomes complex, you need multiple agents. So that's how this multi-agent system works. So when we should use this one? When your task at hand spans multiple domains. So let's say we have transcriptomics, genomics, proteomics, 3 different domains, and so each domain is very different, right? So we cannot have one agent who is an expert of all omics, no, right? We can have multiple agents for each task, like that. And different step require different expertise, and the routing decision benefits from the specialization. So again, the research, analysis, presentation kind of workflow where we can use this multi-agent pattern. So wherever complexity is there, always go for multi-agent thing. But again, when not to use, avoid this pattern when a single agent can handle the task adequately. Because if one person is enough, why you need multiple and creating the complexity, right? Also, when the workflow is linear, like in bioinformatics, let's say for example, you know that after first QC you have to do, let's say, trim galore. After that you have to do again QC. So why you are using three? You can, why not design as a sequential pattern, right? Rather than the agent decide whether I will call this one, then call that one. Why you are disturbing agent, making it more complex? So you can simply say 1, 2, 3, right? So that's what, when your workflow is very simple and linear, don't go with that. And when you have the cost and latency are strict, then don't go with that, because this agent will, play around. It's very random. You are giving complete autonomy to these agents, right? So yeah, so the limitation is like, harder to build and maintain, obviously, and increased latency due to so many coordinations, because this of so many agents are there. And it may happen that your first agent, second agent did, but the inter-agent communication failed, like that. Many complexity are there with kind of this limitation, but the value gain is also there depending on the use case you have at hand. Okay, so let's take an example of bioinformatics use case. So one is like, we have, let's say, 3 agent, clean var agent, very, very special for clean var tasks, Nomad and DB and SAP. Then we have one agent who will coordinate with all 3 and does the, depending on the use case, it will call clean var, Nomad or DB and SAP, like that. Similarly, we can have a drug discovery workflow where we can combine chemistry, biology, genomics. So for example, we have a PDB database, we have, let's say, chemoinformatics, we have proteomics. So that's what, we can have separate agents for each of these domain. Okay, so that's where no single agent can excel across all the domains simultaneously. That's where we use this one. And most of the, nowadays we are at this stage where, most of the real, company use case, you see, they will follow this multi-agent kind of workflow only, design. So yeah, so let's do an hands-on. We'll do an hands-on. Okay, I'll just not open it. I'll open and do the setup, and then we'll reconnect. Okay. Okay, so I opened my VS Code. So I will be using OpenAI framework again to demonstrate this. And again, so if you have not if you don't know how to build that, so I have already created separate video series on using OpenAI framework to build agents, but still I'll go through the code. Okay. So what we need is, like, we need to first import some libraries. So mainly from agents, we need agent and runner, and we need some function tools to define the tools. And I will be using my local Ollama GPT OSS model. So for that, I will be needing these 2 models. And I'm loading my, environment where I have stored my OpenAI key. So this is what I will be using my local model. So I'm defining a client here. This is where my Ollama is running, and I'm using the GPT OSS model. Okay, so let's define the model. So now I'm creating 3 tools. Okay, and we will give each of our agent to each of these tools. So let's say we have one tool called calculate GC content. So given a DNA sequence, basically you calculate how many GC are there, and basically this function returns the GC content. And if you decorate this with this @function underscore tool, then this becomes a agent tool. Okay. Similarly, let's say we have a tool called translate protein, and this, for example, this is a dummy function. Basically, this is protein possible translation sequence is something it will return. If it's simple string, it returns. And we have something called find SNP tool, and it will also give some dummy text. Okay, this is just to demonstrate you, but you assume that in real use case you will have actual code you will write to translate the protein, or maybe finding the SNPs. Okay, so now we have defined our just tools. Now let's create 3 agents. Okay, and now this is our agent. So here we are telling this is the GC content agent. So we are giving the instruction that given a DNA sequence, use your tool to calculate the GC content, and here we are passing the tool, and the tool what we passed is the calculate GC content here, right? So with this tool what we created here, this tool we are assigning it with this agent. Okay, so here we are got the agent here. I will talk like what is this age tool. Okay, so define this first agent, define the protein agent, define the SNP agent. So the GC content agent is linked with this tool. The protein agent is linked with the translation protein function or tool, and this find SNP is linked with the third agent. So now we need a main agent, right? So now you see, to provide some capability to an agent, we need to define the tools, right? So that means this agent is equipped with this tool, but now the main agent also we need to define a tool, and basically we need to provide the tools, right? So we need to convert this agent also as a tool, so that we can provide this agent to this main agent, because this main agent will call this three agent, right, sub agent. So that's what, once you define an agent, you simply call aged underscore tool and just give some tool name and tool description. That means this is now not an agent, basically this is a tool which itself is an agent. So that's where we have now created three tools: GC agent tool, protein agent tool, and SNP agent tool, which in turn are the agents. So now I can give my main agent. So here I am telling my main agent that you are a bioinformatics coordinator. Given a user request a DNA sequence, decide which specialist agent to call, like GC content, protein content, SNP agent. Okay, call the appropriate agent, return the result. Also mention the reasoning behind calling that agent. Why did you call? I am asking you. Let's see it will give or not. And just I am telling answer in 50 words or less. Okay, and here I am giving these three agent. I am linking these three sub agent with this main agent. Okay. So yeah, I have not called this one. I have to call this first. This will fail because this I did not call. Okay, it failed, right? So because this is not defined, so let's define these three agents, three tools here. So defined. So now define our main agent. So we have assigned these three sub agents to this main agent. Now do the call. So basically this is what, with this trace I am now calling what is the GC content of this one. So now you see the question what I asked is GC content. So what, and I am passing this one to the main agent. Now this main agent has three sub agents. One is GC, protein, and SNP. Now this agent will decide, oh, user is asking about GC content, so let me call to the GC content agent. So this main agent will now pass or delegate the task, and delegate that task to the GC content agent. Now this will go to over here GC content agent, which will use this calculate GC content tool to calculate the GC content and get back the response, and then it comes to the main agent, and now main agent got the output and it will use the response and it will respond back to the user. So that's how it works. And similarly, you can also say what is the GC content, and let's say protein, what is the protein agent does, like translate. So now the agent will think user is asking me two queries, so let me use both the tools. Okay, it's not defined trace, so let me do that from agents import trace, because we need to import that model. Okay, so let's run this. So this will open in my trace. So let's go back and let me refresh this page. Okay, so the main agent pipeline. So I will be using my local model, right? So it will take some time. So what I'll do, I'll pause my video, and when it finishes, I'll be get back, and then we can see how does it work. Okay, so it finished the output. So let's see what happened. Okay, so first it calculate called the coordinator agent, right? So we called. So let's see what happens. So this was the system prompt, and here we said that you are a bioinformatician coordinator. Given a user request, you do which agents to call, blah blah blah. Okay, so this is the system prompt. So now the user asks the question, what is the GC content of this sequence? Okay, so now the agent now thinks, reasoning, see, need to calculate the GC content, and we call GC content agent with the input the sequence. So now he thinks that, okay, I need, because of the query, I will need to call. So now it calls the GC content agent here. So now we call the GC content agent comes here. So now you see the system prompt change. So that means we were at this point, we were in the main agent. So now it delegated the task to the GC content agent. So now the control comes here. So that's why you see that if I come over this GC content agent, the system prompt changed, because this one, the system prompt was you are a bioinformatics coordinator here. But if I come over here, we are in the GC content agent, and you see it will say that given a DNA sequence, use your tool to calculate GC content, and the user gave this sequence. So basically this JSON response was given by the coordinator agent to this agent. That's how agent to agent communication happens. Okay, and then you see that reasoning. So now this agent, the second agent, thinks user gave a sequence. We are instructed to use tool to calculate the GC content. So we will call the function calculate GC content. So now this agent thinks that I have a tool calculate GC content. So it calls that. So it called this function call and it got a response 44.83. Okay. So now it sends back the response. It has to now respond back to that main agent, right? So now he says that the GC content of the given sequence is 44.83%. It goes back. So now it comes back over here. So now this is the main agent. Now you see the turn change. So we are now in the main agent. The first we ask the question. It did pass to the GC content agent. GC content agent now call the tool and you got response from here. Then finally this main agent is responding back to the user that, see, I called this agent because the user asked for GC content of the DNA sequence. So why it responded like that? Because in the system prompt we said that also mention the reasoning behind calling that agent. So that's what he provided, the reasoning that I called the GC content agent because user asked for the GC content of the DNA sequence and the agent returned that the GC content is 44.8. So this is what the output you got in the response, what we see on the UI. So this is how you see we just defined one main agent and it assigned that task and assigned or linked that main agent with the 3 sub agent. Each agent now is equipped with its own tool, so they are empowered. So now you can see that how good you can do. Let's say we have a genomics agent and you provide many genomics tool associated with. We can have a proteomics tool who is an expert in the protein related task. We can have a metabolomics metabolomics agent who is very specific to metabolomics task. Okay, and then we can have one bioinformatics agent depending on the query, or we can have multi-omics agent as well, right? Given a, let's say, gene, okay, what it will do, it will query to the genomics agent. It will pass to the protein agent. It will pass to the metabolomics and it will gather the output and then it will integrate and it can do many things. And this is, but overall design philosophy is like that. So you have a coordinator and then it delegates the task to other thing. But the thing like this coordinator agent must be very intelligent. So that's where we should use a very good reasoning model, because he has to break the complex problem into short task and delegate, right? So that's why this agent must be more intelligent in order for it to use. You can have very simple agent for doing this small tasks because GC content, right? Very simple. So you don't need a big GPT-5 model for doing this task. So you can use very small brain, that will be enough. So that way you can save lot of cost, instead of using GPT. See, if I ask one agent to do all the tests, like example, let's say I have one GPT-5 model, very costly model, and I have one agent to do all this thing. That means that agent may run for 1 hour, let's say 10 minutes. So many tokens it will use, it will do that, you will be costly, right? But instead what you did, you use for this one, but you delegated the small tasks to the small agent. They will consume less token and also they will run very fast as well because they are because less reasoning. So that way you can save lot of cost by delegating by child agents, you can say, or specific agent use some smaller model as well. So that's how like the multi-agent design pattern is the most commonly used and most robust system, I would say. So far we have seen all the 6 patterns. So this is the last design pattern. It's very straightforward, human in the loop design pattern. So we will see how we can use human in the design pattern, so that let the agent do the stuff and then the human provides the input and then the agent takes over. So those kind of thing, the between human and agent, how the interaction will happen, that we will see. I hope this was a useful video, and yes, I will see you in the next video. Thank you.